This is your reality check.
Welcome to The Reality Check, the weekly Canadian show that explores a wide range of controversies and curiosities using science and critical thinking. It's April 10th, 2020, and it's just me, producer Pat. Today we have a great interview for you. Christina and I talk with friend of the show and TRC's fifth Beatle, Dr. Stuart Robbins, about what goes into planning a mission to Pluto. Stuart is a research scientist who studies planetary geophysics. We hope you enjoy our chat with Stu and that you're staying healthy and sane, and we'll talk to you soon. Welcome back to The Reality Check, Dr. Stuart Robbins.
Thanks for having me.
How you holding up, Stuart, in Colorado with this new world order that we have?
Oh, I'm just peachy keen. You know, I normally work from home anyway, so nothing has really changed for me other than I'm going to the grocery store a lot less and buying a lot more.
Do you have a shelter-in-place thing happening there?
Colorado has had a shelter-in-place order for a while now. It's a purplish state, which means that it tends to lean Democrat these days, but it could go either way, Democrat or Republican. It's mostly the red states, the Republican states, that don't have the shelter-in-place orders. Like Georgia, I think, and Florida just instituted them. But, of course, exceptions for religious gatherings, which basically is kind of like having a peeing section in a pool. It's kind of like, this isn't going to work.
I am not fond of that term, shelter in place. I like staying at home, but that term is used often with school shootings. Like it already had this meaning about it that's kind of, I
didn't realize that. I've been using it because there are people who are homeless. And so you say stay at home, and it's like, well, what does that mean?
Right. Yeah, that's a really good point. I didn't think of that at all.
So, Stuart, you're working from home, and you're working on something pretty interesting. Can you tell us what it is?
Well, everything that I do is interesting,
right.
But this in particular is a mission to go back to Pluto and beyond.
Oh, is that all?
Yeah. A little bit of background is necessary on this. So the United States has its space agency, NASA. And NASA basically is the main place where you get funding for a space mission or for space research, all of that kind of good stuff. Now, it's fortunately not up to the will of Congress, at least not entirely, as to how NASA divvies up its money. What NASA actually goes by is something called the Decadal Survey. And the Decadal Survey is something conducted by the National Academies, which is an organization which is basically a bunch of scientists doing stuff. I actually don't know that much about it. All I know is that they run the Decadal Survey. The Decadal Survey is kind of what it sounds like. It is a survey done every decade of a couple different fields in astronomy, and they stagger them. So right now we are leading up to the Planetary Decadal Survey. And what that means is that the National Academies has said, we want to write a policy document that is written by and edited by and compiled by the researchers in the field. So it is basically what the community of researchers in the field says, these are what the priorities should be for NASA for the next decade. And so what happens is a bunch of people write what are called white papers. And I think we addressed what white papers are last time I was on, but just in case, for people who might necessarily remember, is a white paper is basically a research paper, but it's not peer-reviewed. So it's basically a policy or an opinion paper, or it's not put through the rigorous peer review process. And so a bunch of people write a bunch of different white papers. Those are assembled by the Decadal Survey Committee for the National Academies. It's published, and then NASA uses that to set funding, decisions, and priorities for the next decade. So if you have a mission concept, a concept that you want to send a mission to wherever in the solar system, because this is the Planetary Decadal Survey, then what you do is you try to write a very strong white paper. You try to get a lot of co-signers onto it, and then the Decadal Survey Committee will review it, and then they will actually rank what the priorities should be for NASA. And your goal is to be in the top 1 or 2 spots. And so what NASA has done that is unique this time for this particular Planetary Decadal Survey is that they opened up a solicitation and said, hey, we want to actually fund a couple groups to develop mission concept studies for the decadal survey so that you can write a really, really good white paper. Because otherwise, people are just really almost literally doing this in their free time.
Right.
And while some people might have a lot of free time right now, whether that's planned or unplanned, it's still nice to get paid when you have to do a lot of work.
Sure. Money helps you,
Right.
for sure.
So what this was is I was part of a team that applied, and we were awarded a grant. It's actually a relatively small amount of money, but it's something. And what this proposal was to write a white paper to study a mission concept to go back to Pluto. And not just go back to Pluto, but to orbit throughout the Pluto system to visit Pluto, its companion Charon, as well as the 4 small moons, do a lot of different fun stuff around there, and then actually leave the Pluto system and go visit a bunch of other objects in the Kuiper Belt, potentially even going into orbit around another dwarf planet. So
Cool.
This is a really interesting mission. This idea has never actually even been proposed before because it was just recently where there was a study that showed that you can use Charon to sort of maneuver about the Pluto system with minimal fuel required. You can actually use Charon's gravity to do this. And you can use Charon's
Gravity assists.
Yeah, right, exactly. I think I know a podcast where you can learn about gravity assists.
Right.
Exactly.
Maybe in 5 minutes or less.
So, Stuart, this is clearly building on New Horizons, I would think, given where the paper's being written and the place that they've chosen. So, did we see something from New Horizons that would make it compelling to go back?
Well, if I may, I did read that the return data made a really compelling case for a follow-up mission.
And that's the goal of anything.
Right.
The joke when I was in undergraduate, when we had a seminar where we learned how to read scientific papers, because it almost requires its own class. Basically, the joke was every paper ends with future work to do. In other words, give us more money to do this thing, because this is only the first step. And New Horizons was really the first step of exploration of these kinds of objects. And New Horizons found that Pluto, especially for a body that's so far out there from the sun, that Pluto is just this weird object that has lots of different terrain. I mean, it has this vast convecting ice sheet, maybe ocean underneath. It has a moon that has tectonics, structures like cliffs that are 20 kilometers high. It has 4 small moons that almost orbit perfectly within the plane of the system. And so how did those form and how did those get to where they are? And one of them rotates so quickly that within a few minutes of the images that we captured during the flyby, we actually saw it rotate a little bit. Actually kind of hurt us because we were planning to compile them together to get a better single image, but because it rotated a little, we couldn't do that. But we learned something new in the process. So basically, every mission is the stepping stone to the next one, and an orbiter is the next logical thing, because with a flyby, you're very limited because you're flying by. You only get a good view of maybe one hemisphere. It's actually a little less because even though you can see half of it, you have a lot of stuff on the limb, and so you don't get as good information from that kind of data. But it's this weird dynamic thing it's a binary system because you have Pluto and Charon. There was some evidence of even interaction, exchange of material between Pluto and Charon. And then, of course, just going off and seeing other objects as well. If you can do that with the same spacecraft, then you save a boatload of money, like $500 million or more. So it's a really cool idea. And so that's why I think we were funded to do this kind of study to write this white paper for the decadal survey.
So I have a million questions, Stuart, but we have limited time. I mean, the first question I would ask you is what goes into thinking about sending a refrigerator to Pluto? Like, what kind of gear do you need on it? Like, it must be so complicated.
That says it all.
Right. Well, so I think I discussed this at some point, maybe on TRC, maybe on 5 Minutes with an Astronomer, that the way that you design these missions is you first come up with what questions you want to answer. And so as a science team, we developed what those questions were. Based on what we saw with New Horizons, what further questions do we have? From there, you go to what kind of observations do I have to make in order to answer those questions? And from there, I mean, it's really basically like designing a laboratory experiment on Earth, except you're sending your lab elsewhere. So from there, once you say what kind of observations do I need, it's, okay, what kind of instrumentation do I need in order to make those observations? So for example, because a lot of people think about pictures, and I like pictures as well, they're pretty and can go on the cover of the New York Times even. So what you can think of with pictures is, all right, I want to make a global mosaic of Pluto and Charon and as much of these small moons as I can. So what kind of camera system am I going to need? Well, that's also going to depend on what kind of orbit I get. How close can I get to the object? Because that determines if I need a very long lens or a very short lens. Then you need to say, okay, well, if I want a global mosaic, but let's say I also want targeted high-resolution images of a couple different things, well, now do I have to have two cameras? Or can I get away with having basically the same telescope but multiple detectors in the telescope that have maybe different pixel sizes? Or can I have the same telescope but maybe a flip mirror that does something similar, maybe sending a light to another telescope for zooming in? And then it's, okay, I want to do this in black and white. Can I also do this in color? Do I have to have a completely different assembly to do this in color? And is the color camera, because there's going to be less light, as soon as you start to narrow down the wavelength range of light, there's less light, and so you get less signal, and so it's noisier. It's like turning up the gain on a speaker system. It's going to sound louder, but the static is also going to be louder. It's the same thing with images. So as soon as I start to split things up into colors, I get that kind of image noise. Am I going to be able to have a camera detector that can split up the light into the colors that I want that also has the noise properties that I want? Or do we not have that technology yet? And so it's really a very linear and yet iterative process where you have to address all of these different things together of what do I want, what can I get away with, what technology do we have that can actually answer these questions, or does that technology not even exist yet?
And presumably the footprint is always a question, right? Like you're looking for the smallest thing at the smallest weight because it costs lots of space dollars to put heavy things into.
Right.
Exactly. So every gram, every ounce, every little bit counts. So that's another big issue, is what is a feasible payload? So we might want to have 20 different cameras. I mean, they're on the Mars rover, so why not? But the problem is that even if we increase the payload by just something like 20 pounds, that increases the time that it takes to get there by a year.
Wow.
So when the numbers were being run, I was like, wait, what? They're like, yeah, it's...
Okay, it's not just us.
I know. I mean, I might be exaggerating it a little bit, but it's not actually exaggerated that much. I mean, we're looking, I think it might have been closer to 100 pounds changes it by a year, but it's not trivial. And you have to then consider the case of, okay, let's say I'm going to get there in 20 years. What kind of power am I going to be able to use out there in the Kuiper Belt? You can't use solar because it's literally less than 0.1%. Actually, I think it's less than 0.01%. It's 1 over 40 squared. So 1/1600th the amount of power that we would get from a solar cell on Earth, we would get at Pluto, roughly speaking. And so you can't use that, so you have to go nuclear. And so the problem with a nuclear power source is that it depletes itself. So if we launch with something like 5 RTGs, which radiothermal generators, so basically the decay of plutonium gives off heat, that heat is converted to power. If we leave Earth with a couple of these, by the time we get to Pluto, we are several half-lives into that decay process, meaning that we will have much, much less power, which means that we won't be able to actually power necessarily all of the instruments that we want. And if we delay getting there by a year because we added an instrument, then we have even less power to use. And that also affects how much data we can send back to Earth. So sending a signal back to Earth requires power. If you have a weaker signal, then you basically want that signal to still be detectable at Earth, and so you have to divide it up into fewer bits, which means then that the bit rate of sending that data back to Earth is going to be less. And that means that even if you have your wish list of every instrument you want, and you have terabytes of storage, which you wouldn't on this craft, but let's say you did, you still might not be able to then send that data back to Earth within your lifetime, or the lifetime of the spacecraft, simply because the bit rate, you don't have enough power to send the signal back.
So, Stuart, New Horizons, which I think was one of the fastest moving probes, for lack of a better word, took 9 years, I think, to get to Pluto. This sounds like it would be much further out.
Right. So New Horizons took 9.5 years, and that was actually a requirement by NASA. It said, your spacecraft cannot take longer than 10 years to get to its target. And it was launched, the fastest spacecraft launched, and it got a gravity assist from Jupiter, so it went really fast. The flyby of Pluto was 14 kilometers per second. That's really, really fast. But yet, even at that fast, look at all the data we brought back. But that data took a couple years to send back to Earth. We would not have that kind of luxury in a orbiter mission, because each orbital pass every couple days, you're recording more data. You don't have 3 years to send it back. And so what we're looking at in order to get there and actually get into orbit, because you have to slow down at some point. You basically spend half your time getting there and accelerating, and then basically turn your engine around and decelerate. We're looking at something in the neighborhood of about 20 years, which is a very long time, but it's still feasible. So in the past, this would have been an impossible mission because A, nobody would necessarily want to be the person planning this mission and then basically be in their late retirement stages when it gets to its destination. But these days, NASA is actually feasibly looking at missions that are in the 50 to 100 year time frame.
Shut the front door. That's crazy.
Well, we're at the stage where some of the questions that we have can only be answered by missions that take that long. And part of the issue is, again, we don't have Star Trek technology. Some of this is driven by simply the technology that we have. And so you have a problem where you might want this kind of mission, but we don't necessarily have the technology to pull it off right now. So we would like to look, for example, at a fission power source, but we can't fly that in space yet. I think there are treaties involved that say you can't, but B, the technology just isn't there right now. And so the rules of this NASA grant, and then, of course, the rules of the Decadal Survey, the rules are you kind of have to use tech that we have right now. And so we'd like to look at some of these more interesting power sources, more interesting propulsion sources, but right now it's just more of a footnote of, hey, if these happen to be developed and flight-worthy within the next 2 or 3 years, that'd be great. But otherwise, this is what it's going to have to be.
So, Stuart, what is happening right now? Because I read that this was being brought forward in early 2020, but considering what's going on in the world, where are things at?
Fortunately, nothing has really changed, at least with this. We've gotten a 1-month delay in when our final report is due to NASA. But otherwise, the National Academy still has their deadline for all of these white papers to be submitted at the end of June. The final NASA report has been delayed because we got a grant. We have to actually also write a report to NASA. That's been delayed until the end of August. But otherwise, the science team as well as the engineering team, we're still meeting weekly. And we're still trying to basically iterate on this kind of problem and all the problems that I talked about over the last couple minutes. The principal investigator and so I'm the deputy principal investigator on this. So we were going to go out to a lab, actually, with the engineers for an intensive 1-week design review where we would go through the trajectory, go through the instrumentation, and try to make all these trades in real time. That was scheduled for in 2 weeks as we're making this recording. That's not happening. So right now, we're still not quite sure if we're going to try to delay it about a month when we might be able to do it in person, or if we'll just do it remotely by telecon. It's not as good by telecon, but it is still doable. So at least for this particular thing, we're still mostly on track, and we're still making a lot of progress. In fact, I just had a telecon about this 2 hours ago as we're making this recording, where we were discussing some of these exact kinds of trades and what exactly we might want to do versus what we need to do in order to make certain observations.
From what I read, the intention was to orbit Pluto for 2 years and then use a gravitational assist from Charon to go to Kuiper Belt objects. Do you have some candidates of what Kuiper Belt objects you'd be interested in looking at?
The place where I work, Southwest Research Institute. Just a quick note, job separate from podcast. This is not affiliated with podcast work separate. That disclaimer in mind, what Southwest Research Institute did was they funded an internal research study led by the PI of the New Horizons mission, the principal investigator, Alan Stern, and they basically worked through a lot of these orbital dynamics to see if this kind of thing was even possible. And so what they did in their study was they also did a study of just what kinds of objects we would be able to visit afterwards to see if it was feasible. So there are a couple different bodies. There are about 15 or so that were identified in the study, including 2 potential dwarf planets that we would be able to go into orbit around after leaving the Pluto system. Now, that initial study done by Southwest Research Institute made a few different assumptions which we can't do as part of this NASA study. So, for example, they sort of assumed we had infinite propulsion. So their cruise time to get between Earth to Pluto was 12 years. That's really not even feasible right now. So we're, as I said, looking more like the fastest would be about 18. It's more likely it's going to be about 20. But other than that, we would still be able to escape the Pluto system and go to most of these objects that they had identified early on. So, I mean, I could throw out some names. You probably would never have heard of them, but some listeners might have. So, for example, Ixion, as well as Quaoar, as well as Varda, and then a few names I can't pronounce, and then some other objects that just have year and letter and number designations. So, for example, 2003 OP32 or 2002 MS4. So these are objects that maybe 1% of your listeners might have heard of, but otherwise they're bodies that are out there. These bodies are anywhere from a couple hundred kilometers across to Quaoar, which is about 1,100 kilometers across. So they're not trivial bodies.
I wanted to ask, do you have a sense of, I mean, I know this is a lengthy process, but any sense of a potential launch date?
There was a requirement that the launch date be in the late 2020s. So this kind of thing, at least for us, the launch date doesn't really matter, except that it has to line up properly with Jupiter in order to get that gravity assist.
Thanks so much for joining us to talk about this today, Stuart. And until next week, think better to act better. Peace out, cuboids.
Stay classy, not smart-assy.
Remember, kids, science doesn't suck, it blows.
For show notes or to discuss this episode, visit our Facebook page and website at trcpodcast.com. For general inquiries or to send a topic or parody suggestion, email info@trcpodcast.com. Help support the show by leaving a review on iTunes and liking us on Facebook. Follow us on Twitter @TRC_podcast.